Hello, 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 hello. Hello, hello, Shivani. I'm audible. Hello. Hello, V Ratan. I'm audible. Please, anybody confirm whether I'm audible or not. Hello, Harsha.
Yes, sir.
No, actually, hello. Hello, I'm audible.
Yes, sir.
Okay, please now once you all confirm. Yes, anybody confirm whether I'm audible or not. Okay, please, as soon as possible, you confirm, then I will start the session. V Ratna, I am audible, or Harsha, Shivani, anybody, please confirm.
Yes, sir.
Oh, okay, okay, thank you. Okay, my screen is visible. On the first slide, week one, hydraulic engineering live TA session. Is it visible?
Yes, sir.
Yeah, okay, thank you. Now let us start. Oh, welcome all in the first live TA session, week one hydraulic engineering. This week is only about the basics concept of fluid, and this is the introductory. First week was the introductory one. So I think sir was covered the several things. Here I will also cover many things. Okay, people are joining still. Good. So for that, I will follow the book Fluid Mechanics in Jalanu Simbala. This is very interesting book. Lots of figures are there for understanding. So I will not start with the definition of fluid because you all know the fluid mechanics deals with the liquid as well as gas both in motion, yeah, or as well as in case of the rest. Why actually we need the fluid mechanics? Because we know the behavior, how the water flow, how water behave, water or liquid or gas, you can say. I am taking the example of water only here. How the gases and water behave So on that basis we design something. If we know the understanding or basic characteristics of the gas and liquid flow, we can design something properly. So this is very very important subject for that point of view. So like hydraulic machines, and you all know the hydraulic machines are based on only the this fluid mechanics concepts. So now, and you also know about the breeze pier in the river and the dam, as well as you can say the barrage, the gate. These all things, before designing these all things, we need the concept of the basic fluid or open channel hydraulics. So these subjects deal with the basic fundamental things of fluid mechanics as well as the open channel. So for that I will follow this Sinjal Simbala book for that. So basically I will deal here with the figures, not very much theories. And also in the last after dealing the theories, I will solve some sort of problem from the previous uh, like 2024, this time 2023 assignments, NPTEL 2023 assignment for this same course, not the another course. Okay, so here the shear force and the normal. Let me ask something. I am audible, people.
Yes, sir.
Yes, yes. Are you getting what I am telling? Everything is fine.
Yes, sir.
Yeah. Okay. Fine. Okay. Now I will move on. Okay. I am writing something. Is it visible? Hello, everyone. Please. Is it visible? Whatever I am writing here. Just I am.
Yes, sir. Visible.
Yes, sir.
Okay. 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 Thank you. So here in the fluid mechanics, the shear force is very very important comparatively when you study about the solid mechanics. The normal force and the shear force and many types of force are important, but in case of the fluid mechanics, uh, the shear force is very very important comparatively. The other force also important, but shear force here play the important role in the fluid mechanics. So before going on the, because we are try what we are going to in the, we are going to do in the fluid mechanics, we are try to formulate the physical phenomena in terms of the mathematics. So if we formulate something in the terms of mathematics, then we can apply anywhere. Until unless if you know about these things will happen, but if you want to utilize that thing in the different places, so you have to understand, you have to some equations like that, so put the variable things and get the another unknown things, so this kind of thing. So for that we need the formulate in terms of mathematics any physical phenomena. So in fluid mechanics we will do entire subject, we formulate the physical phenomena in terms of mathematics. So here shear stress is very very important because in fluid mechanics, as a definition, you know, the fluid when the fluid will motion, when the shear force, any shear force will apply, any amount of shear force will apply on the fluid, then it will be flow. So now here, if the force you apply, let's suppose on a angle, on a theta angle with the horizontal, let's suppose here is the fluid, uh, for your just general understanding I am telling, I'm going to draw. Let's see here, water is flowing, water, this is water, and you have applied some force on that, like you have applied the force, like you are applying the force from here. And why we are taking on the angle, force application on the angle? Because if we derive something on the angle, then if your force is at 90 degree with the horizontal, so you put the theta value is 90 degree. If force you're applying force on any degree, you can put the value. So that's why we approach any force on the angle. So we can uh, if you will apply the force on the horizontal, like the this type, then this is only shear force, there is no normal component. If you will apply the force like that something, then what will happen? One component will be this side and another component will be this side. If this is theta, so your this, if this is f, so this is f cos theta and this is f sin theta. So that is the normal force and this is the shear force. So the this component, that is the f cos theta, is known as the shear force, or if this is the tangent, we this shear force will apply on the tangent of the surface or tangent on the fluid, tangent to the fluid actually. So here definition is what? The normal stress is normal force divided by area, that is this area, in how much, what is the area of this one. If your force is applying on entire area, so you take the entire area A, but here your force is apply only this much area, so we are taking this. Now we are shear force. Shear force is what? The lateral, that is the tangent component of your force acting, whatever you have applied the force on the fluid particle or fluid packet, you can say. So this is ft by dA. So as a stress, you know already, the stress is equal to what? Force by area. So here with apply that definition and here write the these things. Now here the very important line written: for the fluid at rest, if your fluid in at rest, the shear stress is zero. You always remember, if your fluid in rest condition, what will be happen of the shear stress? Shear stress will be zero, because if your fluid have any amount of shear force, it will be flow. But if your fluid is not flowing, that means your shear force is zero, or your tangent force will be zero in case of rest condition. So this is that. Now coming on the next slide, if you want to take the screenshot, please take a screenshot, no problem from my side. Yeah. uh, Please anyone confirm, are you able to understand what I am telling? Anybody please, are you able to understand? Hello. Hello, I am audible, please anyone? Oh, please actually participate in the live session. If you will not participate, then it will be very boring. So please try to participate, because you are far from here, whether I am sitting in the IT Guwahati. So please at least you tell yes, no, whatever you are doing, then I will teach in a different way if you are not getting in this way.
Yes, sir. It's understand.
Yeah, okay, thank you. Because I am teaching only for you and to all of you. Actually, if you will not respond, then whether you know or not know, this is different thing, but you have to at least reply something. Then I will feel I am in class. Otherwise I am telling something and you are not able to getting something. There is no meaning to stay here, and your 2 hours will be, you can say, uh, destroy. 2 hour will be, you will lose. So please, at least you say yes or no. Okay, now moving on the next slide. Okay, in case of fluid and gas, there is a difference. What difference? In case of the in case of the liquid, your liquid having the free surface, but in case of gas does not have any the free surface. So as you know, why the liquid having the free surface and why gas not having the free surface. This is the actually the attraction force between the molecules. So this is the main reason. But now I have some pictorial representation for that. So in figure A, B, C, it is clearly visible. In the A, B, C, the particle in A, the force between the particle, figure A and figure B, if you visualize, in force in figure A, the force is much than B, and if you will compare the B and C, force in the B is much than C, because the particle is far to each other in case of C comparatively B, and similarly in the B, your particle is far from the, from, if you compare from the A representing here the solid, and B represent the liquid, and C represent the gases. So what actually, so you know the, here if you read the line, what it is written, the molecules are at relatively fixed position in case of solid. Okay, in case of liquid, what happened, the group of molecules move about each other in the liquid phase. Okay, in the liquid phase, your molecules move about each other, and in case of gas, the individual molecules move about a random in the gas phase. So here movement happen random. In case of gas, the random movement is happening. And these all things, the random motion and moving about each other, these all things written here after the experiment, lots of experiment, not only a single experiment done and written here, not lots of experiment already written, done by researchers, then written here the your liquid uh, move about each other. Here movement, here random movement, or here each other, move about. And these are the concept you can also see in the some some exams, like you also expect in the gate exam, and also expect in the engineering service exam, also the junior engineering exam, and the state engineering exam. So please, if you are staying here for 2 hours, you try to get more, and if you having any doubt, please you can ask always. So you always remember these things. Now we'll move ahead on the next. Okay, so here the pressure gauge, the figure 1.6 is pressure gauge, and figure 1.7, here the actually it is showing the application of the fluid mechanics. So actually for measuring the pressure we use always the pressure gauge. Let us what is written on a microscopic scale. The pressure is determined by the interaction of individual gas molecule. However, we can measure the pressure on a micro macroscopic scale with the pressure gauge. Okay. Macroscopic scale, if you want to measure something, the macroscopic scale, how much the pressure inside anything, so you just using the pressure gauge you can measure. But if you want to measure at microscopic level what is happening, what is the pressure due to one single molecule, so you have to analyze. So here, and the microscopic scale, the pressure measurement will be based on the individual gas molecules. So here something, the application, what is the fluid dynamic is used extensively in the design of artificial hearts. So your fluid mechanics concepts not only applicable in the civil engineering, also in the medical engineering people are using. So now coming on the next, here you can see the application, lots of application. Here the lots of application you can see, your aerodynamic ship, and here the dam, here the electric, here the medical and the automobile, pipe fittings, wind turbine, and the industrial application, lots of application. But before going application we need to understand the concepts or the basic understanding, basic physics behind it, and based on the physics we need to the formulate or derive the equations so we can apply anywhere. Now coming on the application, the previous applications. So previously, before knowledge of the much in the fluid mechanics, what people was doing, here you can see the for pipeline, that is the segment part of the pipeline here, segment part. But nowadays not segment, if such kind of bend is in the pipeline, so some arrangement, some pipe fitting are currently, in these days the pipe fittings are available. But previous days people not know much about the fluid mechanics, so this type of things you can see. Now coming, and if you want to the screenshot you can take, or I think your, I have uploaded this ppt in a Google Drive, and I think Google Drive will share with you uh, from the NPTEL side, so don't worry. But for sake of your understanding, you can take. So here you can see the Reynolds experiment. This is very very uh, important in the fluid mechanics. This is the Reynolds apparatus. It is visible, I think. So Reynolds original apparatus for demonstrating the onset of the turbulence in pipe. This is the original Reynolds apparatus, and it is being operated by the John Leonard at the University of Manchester in 1975. And here you can also the try, you can see the try by the Wright brothers for the arrow. Now, is someone join or leaving? Okay. So here you can see the how velocity, actually why we are focusing in the fluid mechanics on velocity, there is a meaning, because velocity is related with your other parameters. If you know the velocity and associated with other parameters, then uh, you can get the uh, more knowledge about, because your formulas, because the velocity is very very important in case of the fluid mechanics, and this is the basic parameters. If you know the velocity, then based on the velocity you can derive the several equations. So that's why we focusing on the velocity. And here in the experiment, if you will see, we always draw the velocity like that, velocity diagram. But in why we are drawing like that? Before drawing like that the velocity diagram, lots of experiment was done by the several researchers. That's why we are here. You can see the, this is the solid part, this is the solid things here, this is the solid things, and your velocity diagram like that. In adjacent to the solid, your velocity is very less comparatively, or the free stream or the middle. And so here, so this is the actually experiment done by the, okay, Hunter Ross. Okay, now, so the velocity diagram is like that. So you can visualize from here for your understanding. We will, if water is flowing with the uniform velocity, uniform uh, velocity, so what will, after traveling some distance, your velocity diagram like that. Why? Due to the friction, due to the friction between solid wall, due to the friction between solid wall, here velocity is zero almost. On the surface velocity is zero, comparative zero, and the surface effect propagated upward direction. So your velocity, that is your surface surface friction is propagated upward, but its intensity is, as as you're moving upward, your friction thing, your the bed friction thing moving, effect moving upward, but intensity going to decreases. So what will happen? Your velocity will be here at the surface will zero, because of the here the more friction due to the bed. As you move the above, your friction due to the bed will be less, and your velocity will be little bit high. At moving up to this distance, your effect due to the bed on the fluid is negligible. So that's why from here your velocity is behave, your velocity behave like uniform. So this is the basic things. Why here zero, and here we can assume always, this is the basic assumption in the fluid mechanics, no slip condition. No slip condition. This will very help this concept in your boundary condition or boundary layer theory, and in other like pipe flow, open channel flow, everywhere this no slip condition will be applicable. So now moving on the next. So here you can see the another experiment, the flat plate experiment. The flow on an originally uniform fluid stream over a flat plate, and the region of viscous flow next to the plate on both sides, the inviscid flow. Okay, here you can see this is the plate, this is the plate, and your flow this side. If you visualize here, at this location it is zero, your velocity is zero, and after that your velocity is uniform. So this reason, whatever here, before the, before getting uniform condition your velocity, so this region is the viscous region. Viscous region, why viscous region? Here the viscous force is dominated, that's why the viscous region. And after that inviscid region. And viscous force is what? Viscous force is nothing but force due to the viscosity of fluid. So if you remember, the Reynolds number is what? Inertia force. And what is inertia force? I will explain. Just I will explain, because it is a confusing term. Sometimes people not getting the physical meaning what is the inertia force in case of the fluid mechanics. And now the inviscid, now your viscous force. So viscous force due to the viscosity. So your viscosity is in near the plate, the viscous region, and above the plate, inviscid region. And why we are differentiate these things, viscous region and the non-viscous region or inviscid region, they are the having something meaning. As you will move in this subject further, you will get the what is the meaning of why we are differentiating these two things, because it's helpful, very helpful in the computation part when you will study the fluid dynamics things or computational fluid dynamics. Okay, now here the inertia force. What is inertia force? Inertia force actually force due to your mass of fluid, how much mass is flowing, and the velocity. How much mass and velocity. Force due to mass and velocity known as the inertia force, or nothing but. Now here it is very important thing. You can also see the external flow over a tennis ball and the turbulent wake reason behind. So here you can see one reason. Here you can see one reason. So this is the wake reason. The behind the your tennis ball, this reason is known as the wake reason. This reason is known as the wake reason. So these things you always remember, because here lots of uh, flow characteristics happening. If you will, and where it is applicable these things, just you can visualize. Let's suppose a river is flowing, and in the river, just the breeze pair here, water is flowing like this, the breeze pair here. So if water is flowing like that, the wake region in the downward direction, in the down or in the downstream of the your breeze pair, the wake region will be gen. You can see in the, if you will see, you just type on Google and just try to see the wake region behind the breeze sphere, you will see the all phenomena. And what happened, the your scouring phenomena is happening here. So due to, so this knowledge, if you know these things, then you will design your breeze sphere and all whatever you want to design in proper way. So you can minimize the failure and optimize the cost and everything. Now coming on the next slide. So these are all the examples. If you will see the laminar flow, how laminar flow is happening, how the transitional flow and how the turbulent flow look like. Actually this figure, after the experiment, this figure is were taken. So laminar flow, if you will see the layer wise flow here, you can visualize here the layer wise flow is in the layer form, not any mixing between the layer in the laminar flow case. In the transition case, little bit not as look like the laminar, but in case of the turbulent, the layer is mixing. So based on Reynolds number, you all know what is the Reynolds laminar flow, transition flow, and the turbulent. Let us discuss here. Your Reynolds number is what? Inertia force by viscous force. Now, so Ari, anybody can tell? Just I want to ask to all of you. Anybody know about the Reynolds number? Yes, please. If anyone know, please tell. What is the actually the formula of Reynolds number? Yes, please. Okay, no issue. I will tell. So rho v, and I am taking the pipe flow case. So rho vd is the diameter of the pipe by dynamic viscosity re. So this is a Reynolds number. If your this Reynolds number is greater than or less than equal to 2000, or somewhere it is written the 21, somewhere 23 I have seen all. So you always remember. So it is laminar flow. If it is greater than 4000, so it is a turbulent flow. So always remember in between the transition flow. But here the meaning is what? If your Reynolds number, here I want to take something. If your Reynolds number is, what is meaning? Why the, if the your value is greater than 4000, the flow is, we have like turbulent. In case of pipe flow, here I am taking the example from pipe flow. Always remember. So anybody tell something? Okay. Inertia force by viscous force. For increasing Reynolds number, what you will do? For increasing Reynolds number, let's suppose you want to increase, your value is here 2000, but you want to increase your Reynolds number. What you will do? You have two options. First option, you will increase the flow, that is your mass and velocity you will increase, that is inertia force will increase, and this will be the your viscous force will be constant. This is one way. Another way, your flow will be same, whatever the initial condition was same, but somehow if you will reduce the viscous force, then your re will be increase, that is your Reynolds number will be increase. So the here question maybe anyone can ask, if the initial conditions are same, if you have considered the two case, Reynolds number is, let's suppose 20,000 and another is the 40,000, two case, and your initial condition is same, that is your inertial force is same. So in which case the viscous force will be less, or in which case viscous force will be more? So anybody can tell me, just for sake of understanding. Okay, if your upper part, that is your nominator part, is constant, for increasing re, what you will do? You will decrease these things, that is your viscous force, that is the v part. If you will decrease, so in which case your viscous force will be less. uh, Harsha, are you able to give the answer?
Yes, sir.
In which case the will be less?
Reynolds number is greater than 4000.
No, no, actually you are not getting the question. Okay, okay, let me explain. Because this analytical question you can expect in the gate examination and any other examination. So let me take one new slide. Okay. Oh, Reynolds number here like 40,000. This is the case 1, and the Reynolds number in the another case is 20,000. Okay, this is case 2, and you all know the Reynolds number is the inertia force divided by viscous force. If inertia force in both cases constant, constant your inertia force in both cases, so in which case your viscous force less, in which case, whether first or second. This is simple mathematics. In which case your viscous force will be less.
First case, sir, it may be.
In second case, you are telling in second case your viscous force will be less, right? You are telling in second case or first case?
First case, sir.
Yes, yes, definitely. In the first case, your viscous force will be less, because in the first case, your value RE value is more comparatively in the second case. So if you get the RE more, then what you will do? Only you have one option: the viscous force reduce. So definitely, in the first case, your viscous force will be less comparatively. This. Okay. Now moving on the next thing. Okay, here's some example of the turbulent and laminar. If you will see, actually this is this picture A. If you see the figure number 122, in 122 figure, waterfall is there. Figure A is taking from very near to the waterfall, and figure B is taking from far from the waterfall. The picture is same, condition is same, everything is same. But if you take the picture from far, you will see the laminar type of flow. You will see, but this is not actually laminar. Whether laminar and the turbulent, it will depend. After the, if you will visualize, you can tell the after visualization easily you can tell the laminar or turbulent. So this is only the qualitative understanding. So from the very far distance, you cannot tell the whether the flow is laminar or turbulent. In the figure 21, what is actually in this Silerian image of a girl in a swimming suit, girl having wearing the swimming suit, the rise of lighter warmer air adjacent to her body. If you will see here, the water, the warmer air is rise up near the body, not this side, not this side, but near the body is rise up. So what is again written? Indicate the human and warm blooded animal are surrounded by thermal plumes of rising warm air. If anybody having the warm blood, like any animal or any man or woman, what, so always, as per the fluid mechanics visualization or experiment, always warm air will be increasing. Warm air, what is written here? Rising warm air near the surrounding of the body. So that's why uh, if you will visualize, if in case of consider thinking, just you think, you are sleeping on the bed, and if you are not having any uh, any blanket on over you, what will happen? There is no only cool. If you will have some having the blanket, so you will feel the warmer. So this is this you can visualize, just for your interesting point of view I have taken. So now the wake reason, what I was telling the previously, here you can also see the wake reason. If or you can also see the wake reason in the of sea flow or the navigation in, if you are near any river and the navigation thing is happening in this river, you can see the behind the ship, you can see always, or behind the boat you can see the wake reason. So now from here it is very important, this diagram is figure 1.24 is very important. So what is actually figure 1.24? How many students? Okay. So what is representing the figure 2, figure 1.24? So initially your velocity was uniform. Your velocity here, your velocity was u, and here also your velocity was u. This is, just assume the condition. But after moving, these are solid walls. These are the solid walls. These are the solid walls. That is the friction walls. The wall having the friction. After moving some distance, your velocity diagram is like that. Here was uniform, but after moving your velocity, suppose the length of the arrow represent the velocity magnitude. Near the here, after moving certain distance, your magnitude of the velocity is reduces. Why reduce? Whatever I have explained earlier, due to the friction of the bed, due to the friction of the your, this is the pipe, this is the friction of the pipe wall. So after moving, the your velocity is behaving like that, and after moving it is improving, like here what was, if you will see the uniform velocity distribution in case of depth, here it is the, let's suppose this is x direction, this is y direction, y, this is x, not y, this is x. So here the depth of your uniformly distributed is more, comparatively here depth is less, comparatively here depth is less, and here is the depth is 0, the your uniform distribution is 0. So up to that much distance from uniform to getting the fully, or you can say the fully, after that your velocity diagram uh, will not change. Here after that you will see your velocity diagram like that, here also velocity diagram is like that, never will change your velocity diagram in the x direction after that. But up to that, this distance is known as the development length. Development length, always remember what is development length. So that's why if we conduct some any experiment, so if you will conduct some any experiment, so what you will do, you always you try to measure anything after the development length, not in the development length, because the you have see here the velocity, your develop uh, velocity diagram is as you moving in the x direction, velocity is keep changing up to the development length. So you cannot measure accurate thing what is happening. And for calculating the development length, lots of formulas are there, lots of, in case of laminar, or in case of turbulent, what is the development length formula. Whether I don't know, here I have written, oh, I have written in the next week class, so here I have not written. I will discuss later, or you can search on the Google also. And now, okay, development length is here. So control volume, I think control volume thing is covered or not. Let me uh, control volume thing is covered or not in class. Hello. Hello. Hasa. Okay, I think facing some network issue. Okay, no problem. Now moving ahead. Okay, control volume is nothing but we always in case of the fluid mechanics, uh, we always apply the conservation laws on the control volume. Why? There is a reason behind it. Because in case of solid, if you will see, first try to understand what is surrounding, what is system and boundary, then I will explain the control volume things. What do you mean by control volume? Later we'll discuss more about the control volume. So surrounding here, this is your system, and this dot dot thing is your boundary, and beyond the boundary is your surrounding, everywhere surrounding, and inside your the boundary, this is the whole system. So your control volume is what? Some volume, just for sake of understanding initially, some volume in the space, some volume in the space, this is your control volume, just to remember. Because control volume, or here you can say a control volume with a real and the imaginary boundary here, something, this is the imaginary and your real boundary is this, so this is the control volume. Some, always you remember some volume in space, so this is control volume. And what is the concept behind it, why control volume is applicable in the fluid mechanics, and why it is very very important, we'll discuss later on that. Your control volume may be fixed, may be moving, both type of you can see the control volume, real or imaginary boundary also. Now moving on the next. So what I was discussed before in the first slide, why we need to study the fluid mechanics, and why and how this physical phenomena we formulate in case of the formulate in form of mathematical equation, and why mathematical equation is important. Because if you will not formulate in mathematics your physical phenomena, will not able to design anything. And after the mathematical formulation your physical problem, you can optimize the things, and you can save also the hazards related with the fluid mechanics. So now the physical, if you having how we proceed the mathematical modeling with your from any physical problem. So initially you have any, let's suppose a physical problem, what you will do after, if you have any, this is very very important concept, how we move from physics to mathematics. You have any the physical formula, Then after, identify the important variables, which variables independent, which variable is dependent for any causing the physical problem. Now after that, make the reasonable assumption and approximation. Then after, because assumption and approximation is needed, because you cannot derive any mathematical equations with all physical conditions, so that's why it is important. Apply the relevant physics law, maybe conservation of mass, conservation of momentum, conservation of energy, whatever relevant, which one is relevant. After formulating your physical problem, you can, based on that physical problem, you select your relevant physical laws. Now after that, this using the variable and physical law, your differential equation will come. And after the differential equation, for solving the differential equation, you know, the lots of in numerical techniques are there. Directly, some equation you can solve the directly differential equation, but some equation you cannot solve, or very uh, need very computation for solving the direct. So numerical techniques are there for solving. For solving these differential equation, the numerical techniques are there. You always know the Euler method, Rangakuta method. No, so many things, so many methods are there, techniques are there. Then after, apply the boundary condition. What is your boundary condition? What is the boundary condition behind your problems, and what is the initial condition from which, because why initial condition is important. Let's suppose you want to solve any problem. This is open channel, and here the bridge pair is there, and you want to see, due to this bridge pair, what is happening in the channel. Before channel was there, but after putting the bridge pair, what is happening. So what you will do, first you will, your differential equation you will know. First you will formulate some mesh kind of thing. First you formulate mesh kind of thing. What is I am telling, you will get, just for your understanding I am here drawing. You will draw the node. And why node? This is the reason, because the, for solving these techniques are solving like that. In the node you will solve the equations, in the node you will solve the equations. Each and every node you will solve equations as you propagate it downstream, and you will get some result on that. And then after, for solving these equation, you always need the initial condition, like what is your initial velocity, what is your initial pressure, discharge, everything is needed. Then after utilizing the equations, your, let's suppose your initial, at that maybe your velocity will be increases, at that maybe your velocity, stream velocity will decreases, whatever. So now coming on the next thing, how people approaches this concepts, physical to mathematical. If you will see here, the actual engineering problem, what the aeroplane, but simplified body of the aeroplane is what, simplified body here showing the your aeroplane body, and your rotor disc here. If you will see the rotor disc is showing this one. So simplified the problem and assumption and the approximation, and try to understand what is happening around this body. So based on that we'll design something. Now coming on the next, if you will see here the fluid mechanics application, before that and after the streamline like that, your body like that. So here the more air in this type of body, more air resistance here, the streamlined body, so it will be less. Similarly, like that, the what is continuum and all. So before applicable any mathematics law, we need to the continuum things, because mathematics itself having some principle before validate before validate the principle of mathematics, you cannot apply anything. The mathematics you cannot apply in any subject. You have to the verify the basic principle of mathematics. So in this regard, in case of fluid mechanics, we need the continuum things. Just for sake of your understanding, what is continuum? Continuum is what actually, if you will see here, it is very in a fluid. A fluid is composed of molecules which may be widely spaced apart, especially in case of gas phase. In case, I think in the first slide or second slide, or maybe the third slide, I have shown you the gas, the difference, the distance between the particle in case of liquid or in case of the gas. So here it is written only. Yes, it is convenient to disregard the atomic nature of the fluid and view it is the continuous. Okay. So here what is written? Yes, it is in actually it is having the distance between the particle, but homogeneous matter, but we consider here what the homogeneous matter, and there is no hole between the particle, like your particle is like that. But what we are going to consider using this assumption, that is the continuum assumption. Why continuum assumption? Because we need to the formulate your physical problem in the mathematics, and applying the mathematics you always need the continuum. So this is not everywhere, but here you need the continuum things. There is no gaps between the particle, we are going to assuming. So I think with this assumption there is no harm to assume these things, because the distance is very less, this distance is very less comparatively. So there is no harm to assume that there is no gap between the particles. So this is the continuum. So these things we know the continuum. After moving ahead, you will know about more the continuum. Some extensive property, here it is written the extensive property and the intensive property. So it is also important what is extensive and what is intensive. So anybody? Okay. After that, so the time is okay. How many slides are there? Okay, so many slides. Okay, after that, we have the questions. Okay, no problem. So what is intensive property? Intensive property are those that are independent of mass of the system, such as your temperature. Your temperature is not dependent on mass. Your pressure, your density, these are the independent, these are the intensive properties. Or extensive property is what? Which is depend on mass, which is depend on size or extent or system, like total mass, total volume, total momentum, or some example of the extensive properties are these all. So now moving on, the you know the extensive property. What is intensive property? Your intensive property is not depend on mass, and these things we need in the next chapters. So these are the only value. What is your SG value, that is a specific gravity. So you can take the screenshot also, or I have uploaded this PDF already. I have uploaded. Okay, now there is no meaning. Now coming on the very important thing. So some here important thing, your the graph between, actually Newton's law of viscosity, you all know tau is equal to rho mu du by dy. This is your Newton's law of viscosity, that is your shear stress is equal to dynamic viscosity and del u by del y. That is the change in velocity uh, in the y direction. These things let me draw for your understanding. If this is y direction, so change in velocity, this is how velocity is changing. Here the velocity is this much, here the velocity is more, here the velocity is more, so that is okay. So here if you will calculate u is mu is equal to what, from here your tau divided by this whole term will be in the denominator part, du by dy. So that is written here. If you will consider a, tau is your corresponding a and this is b, just for assumption for sake of understanding. So your diagram is like that. For water, this is for air, like that. For oil, these all lines are drawn, are based on the experiment, not uh, qualitatively drawn. So this for Bingham plastic type of fluid, this we have. Always remember, sometimes in the exam this kind of thing examiner expected to from your side, because this is basic, so you remember. Okay, what is written actually here, if you will see, the variation of shear stress with the rate of deformation for Newtonian and the non-Newtonian fluid, the slope of curve, actually the slope of curve is your the variation of. Okay, now, or this is the application of your viscosity, actually where is you will apply the viscosity application. So in the, actually the cylinder, if you want to calculate the viscosity of any fluid, so this is example is there. What you will do, this is the cylinder, one inner cylinder is also there, and in between the fluid, and you try to rotate these things. If you will rotate, some equation will form on that basis, this type of equation will form, and on that basis you will calculate the viscosity of the fluid. Like you want to put here oil, for oil you will calculate the viscosity with this kind of experiment. Or you want to put here the glycerin, if you want to calculate the glycerin viscosity, you put here the glycerin and rotate, and applying this formula. This formula also derived based on the lots of assumptions. So you will calculate the viscosity of glycerin, whatever. If you want to calculate any viscosity, you put between this and rotate, and calculate the all these parameters, then you can calculate all these things. Okay, so I think capillary rise and fall you all know. So this is one question is there. If you want to solve, anybody, please try to solve this question. It is very very important. Okay, so before moving capillary things, you all know. So water is here. If you will see, the water is a wetting fluid. Why wetting fluid? The meniscus is upward direction. So this is the wetting condition, so that is the wetting fluid. Just for name sake of name, non-wetting, here your mercury is lower meniscus, so what will happen, your upper surface, your top surface is not touch the these things, your outer boundary, so it is non-wetting kind of fluid. This is actually in the nature of mercury. Okay. So height of capillary rise, you will see here the formula. This formula is height of capillary rise. You all remember these things because sometimes this is small formula can ask in examination. Okay, the time is 7:11. So we'll solve question. Before moving the question, I want to show you the previous question of this. Okay. So now we will see the questions. Now we'll go in the folder. The assignment 1 is this. We have 10 questions from the previous hydraulic engineering course, NPTEL course. So we will solve some the previous year NPTEL questions. Praveen, slide is visible to you. Hello, Praveen. Praveen, slide is visible. Okay, first question is this. Let me ask whether it is visible or not. Okay. So the first question is this. The question 1 is about a fluid occupies a 12 meter cube volume and calculate the specific volume in kg per meter cube if the fluid mass is 8 kg. So, okay, let me take the pen. So, your mass is given 8 kg and your volume is given 12 meter cube. So, it is asking the specific volume. Specific volume is how much? So, specific volume is how much? I think in solution we have some here if it is written volume, that is your meter cube, and here it is a mass, that is kg. So what will here unit should be your meter cube by kg. As per the unit, this question is wrong, I think. Okay, but now moving. But your specific volume is what? Volume per unit mass. If volume per unit mass, how much volume? Here I think meter cube per kg. So what we will do? A specific volume. You can check also in the book what is the formula actually. If volume divided by your mass. Volume is how much? That is 12 and this is 8. Okay, so 0.5 meter cube per kg. So this is a D option is for that. If formula is this. Okay. Now the question 2 is an ideal fluid is anybody join or not? Okay, ideal fluid. Now an ideal fluid is just please guess, then I will tell the answer. Take 1 or 2 minutes for that. The option A is non-viscous and incompressible. Option B is viscous and incompressible. Option C is viscous and compressible. Option D is non-viscous and compressible. Which one is correct? An ideal fluid actually. We are talking about here ideal fluid. So ideal fluid is non-viscous and it is compressible or incompressible. Two thing is incompressible. So here inviscous means your viscosity is 0 and incompressible means what? Fluid you cannot compress, density constant always. So option A is correct for that. The detailed solution also given. You can go through, just you can see the detailed solution what is written. An ideal an ideal fluid is the kind of fluid that has no viscosity and is incompressible. This simply means that an ideal liquid is a non-viscous liquid that contains zero tangible forces among the layer of liquid in relative motion. The density of liquid remains the same even after the application of pressure. To understand it is better, let's look at some properties. Okay, this is I think. Now moving on the next question. Now moving on the next question, question number 3. Okay, I think someone Tirumlai, the question is visible. Question number 3. Tirumlai, I'm audible.
Yes, sir.
Yeah, question 3 is visible.
Yes.
Yes, please try to solve the question number 3. You have the
Yes, I will try.
yes, you
I
have
will try,
3
sir.
minutes. Let me read the question. What is actually the question number 3? A small shear force is applied on an element and then removed. A small shear force is applied on the element and then removed after applying. If the element cannot regain its original positions, what kind of an element can it be? Solid, liquid, fluid, gas.
Option D, gas, sir.
Okay, you are telling the option D, huh?
Yes.
Okay, so what is question is written here? A small shear force is applied on an element, right? And
Yes.
then removed. After applying, you will remove this force. If the element cannot regain its original position, what kind of an element can it be? So actually, uh, what I am telling. Okay, you are telling the option number B, right? D, right?
Yes.
But not here. The option number fluid, because fluid is a combination of both your liquid and gas. In case of solid, it is possible. In case of solid, it is possible. You, if you applying the force, let's suppose a solid body like that. If you are applying some force here, so it is possible to, after applying the shear force and after removing the shear force, it is possible to regain the shape. But in case of your gas as well as liquid, not possible. So best option is representing fluid, right? Always
Yes,
remember.
sir.
Always remember. So here what is the explanation is here. Actually these questions from the previous 2023 hydraulic engineering course, right? This type
Yes.
of questions you can expect in your assignment. In your assignment 2024 hydraulic engineering NPTL, right? So that's why
Yes, sir.
yes. So here the detailed solution is what? The fluids, that is liquid and gas, cannot resist even a small shear force and gets permanently deformed. Hence the element must be a fluid element. So this is the explanation is there, what I was telling. So question number 4 is this. Where is option D? Yes. So question 4 is visible?
Yes, sir.
Yeah. A hydraulic press has a ram of 30 centimeter diameter and a plunger of 3 centimeter diameter. Okay, it is used for lifting a weight of 60 kilonewton. Find the force required at the plunger. Oh, this is the question. One plunger is there. Let's suppose if you are like that, here in this end some weight is there, like one, you just imagine one car is there, right? And you want to,
Yes, sir.
here some plunger is there. This is the plunger. and in between the fluid is filled completely, fluid filled throughout the. So how much? And the weight of lifting is 60, that is your W here, 60 kilonewton. Air force, how much you need? This is the question. This type of question you can expect in the your examination also, final NPTEL exam, or also competitive exam you can also expect. So please try to solve this question.
Yes, sir, I will try.
Yes, yes, you try. Yes, please solve just. Okay, now we'll discuss the solution part. So this was your problem. Now, uh, you want to tell something? So here, what you will, yes. So solution is this. Both side pressure, actually, this side your diameter, it is visible here. Your diameter is 3 centimeter, and this side your 30 centimeter. It should be more wider, like that. It should be more wider. This wall should not be there. It will be more wider, like this,
Yes, sir.
30 centimeter, right?
Yes.
So in the question is here written, this is your plunger, what I was telling previously. So plunger diameter is 3 centimeter, right? And a hydraulic press has a ram of 30 centimeter
That
diameter.
is centimeter.
Yes, this diameter is 30 centimeter. So what you will do, pressure in both side will be same. P1 and P2 will be equal as per the Pascal law. I don't know Pascal law is covered or not in the basic things, but here question is, so that's why I'm explaining. So pressure is equal to what? Force by area. So here F1 by A1 is equal to F2 by A2.
Shear stress.
Yes, not shear stress. Here the pressure. The pressure definition is also the force by area, right? Shear stress. Stress is also the force by area, right?
Yes, sir.
Yes. So force is how much you want to calculate the F. This was F. You want to calculate area is pi by 4 into
Pi d square by 4.
0.03 square, right?
Yes.
And here F2 you know already, that is F2 your
60
weight.
kilometer.
Yes, so I want to put it in Newton. So 3 divided by area pi by 4 into 0.3, right, square.
Yes, sir.
So after
0.03 square, sir.
0.03 this side because the 3 centimeter diameter, and this side 0.3 because 30 centimeter, right?
Yes, sir. Okay.
30 centimeter divided by 100, it is how much? 0.3 meter, right?
Yes, sir.
So after calculating you will get 6 0 point how much, 0.600 kilonewton. So just you can see, it is very interesting using this concept, using this simple concept. A 60 kilonewton weight, 60 kilonewton weight, you are able to, you are able to lift only
Lift.
0.6 kilonewton force, right? If anybody
Yes, sir.
want, if you have not this concept, if you're not the fluid mechanics concept, and even people don't know the fluid mechanics concept, what people will do, people try to lift this by hand. But for lifting 60 kilonewton, if you are applying your hand, you need 60 kilonewton or more for lifting that. At least you need the 60 kilonewton, your hand should be able to lift. But
Yes, sir.
after this application, your 60 kilonewton, so how much, if you want to calculate how much you have saved the force, how much, okay, are you able to give the answer? How many, how much times? Like 60 is equal to x time of, like y time of 0.6. We will calculate here how
Yes,
much.
sir.
60 by zero point 0.6, that is 100 times.
100.
Yes, you have applied the 100 times less uh, force for lifting this thing. So it is very very interesting and motivated. Now coming on the next question. Okay, is it visible?
Yes, sir. Visible, sir.
Yes, please try to solve.
Yes, sir. I will try.
The question is the equivalent head of mercury corresponding to 4 kilopascal is. The specific gravity of mercury is given 13.6.
Sir, I will try to solve.
Yes, yes, sure. You have the 3 4 minute. Then after I will show the answer and explain what is actually the meaning. The equivalent head of mercury corresponding to 4 kilopascal. So what should be your approach by using the by using the properties of mercury? You try to equivalent, you try to equate your pressure, that is the kilopascal, equate the some with the properties of mercury.
Sir, option A 3 centimeters, sir.
Option A, huh? Okay, let me see. Yes, option A is correct.
Yes, sir. I got.
Yes. So here approach should be what your, so you know the one thing. What is your pressure is equal to what? Rho gh, right?
Yes, sir.
In case of hydrostatic.
So, but I used to do pressure equal to gamma H formula, sir.
Just you try to understand. The
Yes,
hydro
sir.
in case of hydrostatic, your pressure distribution like that, rho gh, right? And what is rho g? Rho g is nothing but your unit weight, right?
Yes, sir.
That's why here the pressure is equal to what? Your gamma h. Getting? Got it?
Yes, sir.
So
P equal gamma H.
yes. And what is your gamma? Your gamma is nothing but rho
9
g.
9810.
Yes. So
Specific weight.
no, no. For rho, for mercury, here you need to apply the 13.6, right?
Yes, sir.
In case of water, you will 1000 you can take.
1.
Yes, kg per meter cube. But rho for here 13 point specific gravity and multiply with the 1000, then kg per
Yes,
meter
sir.
cube. Okay, so this is the basic concept. Always remember.
Yes, sir.
Now moving on the next question. Question number 6. The specific weight of question 6 is what is the, where it is.
Sir. Option B dissolved salt
Yes, it is written here the specific weight of seawater
is more than that the pure
is
water.
more than that of the pure water because of it.
Yes,
Yes.
sir.
So what is the reason? Can you dissolve air, dissolve salt, suspended matter, or all of the above?
All of the above, sir.
Yes, you have the sea water and you have
Yes.
the pure water. Why the specific weight is more? Because all of them here, because the suspended matter is there, let's sand is there, right? Dissolved salt also is there, air is
Yes,
there,
sir.
so that's why it is okay. All
Yes,
of the
sir.
above this question. So it is a general question. Now moving the question number 7. This is very very important.
Density.
You can expect this question in the many examination also. Which one of the
Sir,
following? Yes,
option A meter. Option A, sir.
you are telling the okay, okay. I will
Yes, sir.
explain also how the option is. Which one of the following?
The unit of mass density is kg per
Yes,
meter cube, sir.
mass density. Okay, let me explain little bit. Mass density is nothing but rho, that is
Yes, sir.
mass by volume. I want to write the full.
Mass is known as kilogram.
Okay, so mass is kg and this
Yes, sir.
is your meter cube. If you will represent in, so this is m
Power 1.
and this is L. Okay, so M L L cube actually.
Yes, sir. L cube m power 1.
L cube. Yeah, you can say M power 1 also.
L power minus 3.
Minus 3 because from this
Yes, sir.
denominator to nominator. And here the in all option T is there, you can also put the T, no problem. So which option is correct? Option A is correct for that.
Yes, sir.
If you want to calculate the uh, dimensions of this
Sir, your voice is
dynamic
not
viscosity or kinematic viscosity, can you please tell me?
kinematic viscosity equal to viscosity by
Yes, viscosity by what is?
mass density.
Yeah.
Rho.
So what? Yes. Good. Good. So what is your dimensions? Just please try to solve. Let me move ahead on the next question.
Yes, sir.
Yes, please solve and tell me because it's a kind of practice. Maybe in the coming assignment you will maybe see this type of question
Surface
also.
tension.
So your mu is equal to dynamic viscosity and rho.
Yes, sir. Viscosity unit Newton second per meter square. Just
What you are telling?
Newton second per meter square.
Okay, you know. Let's suppose anyone not knows, so what he will do. Let's suppose tau is equal to this formula everyone know.
Yes, sir.
So from here,
Newton
and this stress is equal to what? Force by area.
Newton law of viscosity.
Yes, this is Newton law of viscosity, and this is your velocity.
V
I'm going to write in this way because I'm going
distance
to find
y.
out the dimensions. So this is Newton. So here you can also mass into acceleration, area, mu, v and y. Now you put the dimensions here. Mass in kg,
Kg
meter
per
per
meter.
second square,
Meter. Yes, sir.
meter square
Yes, sir.
equal to, you want to find out the mu, and this is meter per second
Meter
and
per
this is
second.
meter.
Meter.
Meter cancel.
Yes, sir.
Here 1
Second.
second and this second is cancel.
Yes, sir. Meter square.
What is happening? Yes, meter and this meter is cancel. Right. So
Yes, sir.
how, what is remaining? Kg
Kg
divided by meter
meter second.
second This is remains only, huh?
It-
Anything remains? No.
This is for mass, sir.
Yes. Right.
Yes, sir.
So in terms of dimension, what you will write here? M L minus 1 T minus 1, right?
Yes, sir.
This is correct, huh? Okay, from here your mass cancel.
Meter, sir.
Yes, here
L
what?
T power 1, T power minus 1 by L power 4.
This is correct.
Yes,
The
sir. Correct, sir.
this is kinematic viscosity dimension is this.
Viscosity. Yes, sir. Meter square per second.
So this is wrong, na? This is wrong. Meter square per second means L square T minus 1. Okay.
Yes, sir.
Where we are doing mistake, let me check again.
Yes, sir. Kinematic distance.
Yeah. Where we are doing mistake, are you able to find out? Stress is equal to, we have right, everything is fine. Shear stress is equal to force by area, that is force is equal to mass into acceleration, and your area is there, right? Mass in kg
Sir, second square.
meter per second square. This is your meter square, okay, and the meter per second, and this is meter cancel, and here second is cancel. Now meter cancel, so kg meter second. We are doing some mistake, I think.
Sir, second square not coming here, sir.
Yes, the acceleration unit is what? Meter per second square, you know.
Yes, sir.
Okay, let me, tau is equal to mu. I think we are velocity into y. This is formula, right? So this is, I think it is okay. Here okay, I think we are doing mistake here, some putting. Oh, we are here.
Force unit.
Yeah, here we are doing some mistake.
Yes, sir.
What was your already L cube is there, right? This
Yes,
thing
sir.
you put here. Your kg mass and 1 meter is below, right?
Yes, sir.
That is L, and 1 second is there. So mass cancel. So L4, L4 by T minus 1. So this is like that. But unit is what? Kinematic viscosity.
Meter square per second, sir.
Yeah. So L square by T. This should be.
Yes, sir.
How, where we are doing mistake?
Sir, force unit is Newton.
Yeah, but you need to convert in the Newton in case of mass, in terms of mass, right?
Yes, sir.
So mass, force is equal to mass into acceleration, or stress is equal to force by area. It is Here we are also doing very good, no problem. Where we are facing the problem, let me try in another way. It should be not like that. Tau is equal to mu u by y. So mu is equal to what? Tau into y divided by your velocity. So this is what? Newton per meter square into meter square. Here I am writing, and here meter
Sir,
second.
we will try to another method, sir. Kinematic viscosity nu equal to mu by rho.
Yeah, it's okay. Let me try another way. Okay, so here your meter cancel. So Newton second per meter square.
Meter square, yes,
This is
sir.
the unit of this, right?
Viscosity.
Yes. So what is Newton? Newton is kg into acceleration. That is meter per second square, right?
Yes, sir.
And another second is here. 1 second cancel, 1 meter cancel. So kg meter second is there.
Yes,
So
sir.
here
We
what you
will
will,
try to nu equal to mu by rho.
here what you will, yeah, mu is
Yes,
equal
sir.
to these things, that is kg
Yes, sir.
divided by your meter second, and rho, that is your kg meter cube. Yeah, it is coming, no problem.
Yes, sir.
Kg per meter cube, and this will goes up. So your meter cancel, and kg cancel. So meter square per
Yes, sir.
second. So here L square by L
Kinematic
square, or T
viscosity.
minus. Always remember.
Yes, sir.
Sometimes we have not visible where I was doing mistake, but try to another way. No
Yes,
problem.
sir.
So the question number 8 is, what is the surface tension? What surface tension? Act in a plane of the interface normal to any line of the surface. Yeah, it is correct. Option A is correct for that. Now moving ahead on the next
Yes,
question.
sir.
Question number 9. For an incompressible fluid, does density vary with temperature and pressure? This is the question. For incompressible fluid, here the condition is given a fluid,
It's known as water, sir.
but it is incompressible.
Water.
What you are
What
telling?
is water, sir? Water H2O.
No. Here the question is like that, and you need to select the option A, B, C, D. For an incompressible fluid, does density vary with temperature and pressure? That for incompressible fluid is there, right? For
Yes, sir.
incompressible fluid, some density will be, is the density is vary with temperature, whether with temperature this density will change, or if whether this density will change with pressure. This question is there, increase or decrease, whatever, with temperature and pressure, this density, the incompressible fluid. So it varies for all temperature and pressure range, it remain constant, it varies only for lower value of temperature and pressure, it varies only for higher value of temperature and pressure. So you know, for incompressible fluid, what the meaning of incompressible fluid is, what the your density is always constant, right? So
Yes,
you
sir.
always remember your density will be constant because it's a incompressible fluid, right? But
Yes, sir.
if fluid is compressible, then the scenario will different. With temperature increase with the pressure, the scenario will be different. Now the question number 10, this is the last question. Okay, the depth of center of pressure for a rectangular lamina. Lamina means nothing but, lamina means There is a three dimension in any uh, let's suppose a three dimension consider, but in case of lamina only two dimension is more, comparatively three dimension is very less, so that is the lamina. A rectangular lamina of height h, the height is h. If lamina, if you want to draw, this is lamina. So height is given how much? Height is given h. Now width b, width is given b. Width is given b. If you are dealing with lamina, what will be your lamina like that? Your body will be up to that much only, up to that much, not this much, because it's lamina. So your height this much and your width this much, not this much, because your third dimension should be very less. Okay, immersed vertically in the water and its longest edge vertical and top edge touching the surface. So what is the center
2
of
into h
pressure?
by 3, sir. Option C.
Yes, if it is like that, your lamina, here is B and here is H, and top is touching the surface, immersed vertically, this vertically, and okay. So this figure is not applicable for this. Okay. So now what will happen? So your center of, this is the center of gravity, and center of pressure will always lie below the
Yes, sir.
center of gravity and center of
Center
pressure.
of pressure. CGC.
You are telling the C, right?
Yes, sir.
Okay, let me check. Yes, C option is correct. For the formula is what? The center of pressure formula Ig divided by AH bar plus H bar. H bar is nothing but height up to that much. In this
Yes,
case,
sir.
H bar is
You know that
height.
the x bar by 2. Yes, sir. X by
Yes,
2.
H by 2. And your Ig is what? The moment of inertia.
Moment of inertia of the figure.
Yes. So moment of,
BHQ by 12.
yes, BH cube by 12. So putting this value, and area you always know,
Area.
B into.
BH.
Are you getting the what is the meaning of lamina?
Two-dimensional
Yeah,
figure.
two dimensional. Okay, because this is a lamina, right?
Yes,
But
sir.
this three dimension thing is very small. Like some thickness is there of the body, but is very comparatively small, right? So
Yes,
you
sir.
can consider the 2D. So with that, oh, question 11 is also there. How many questions? Question 12 is also there. So kinematic viscosity is expressed meter square per second. We
Meter
have
square by
discussed
second.
already.
Yes, sir.
And what is the question number 11? The hydrometer is used to determine what? Hydro means what? Water. You all you know. And meter means. So what is use of hydrometer? Zero relative humidity, surface tension of liquid, specific gravity of liquid, or
Viscosity
viscosity
of
of liquid. Which one? For hydrometer, which what you can find out using the hydrometer. So a specific gravity of liquid you can find out. Some explanation is there. A hydrometer is an instrument used to measure the specific gravity or relative density of liquid, right?
Yes, sir.
That is the ratio of density of the liquid to the water. That is your the definition of nothing but the specific gravity. The density of liquid and the density of water ratio. Specific gravity ratio of density of any fluid.
Standard density of liquid.
Yes, and the your water here, H2, H2O, right?
Yes, sir.
So it's all about for today. We'll meet, I think, on the next Tuesday. Okay.
Thank you, sir.
Okay, thank you. Harsha, what about you? You are getting something? You have got or not?
Yes, sir.
Okay, in between, I think your connection was lost, right?
Yes, sir.
Yeah, no problem. You just go on the. I will upload this video in one channel, and that I think link will share with you from the NPTEL side. So you go again with this video, right?
Sir, you can share the previous video link.
No, this is the first class.
No, sir. His name is Ashwini Tiwari.
No. Actually, I am taking this session. I am Om Prakash Maurya.
Okay,
So
sir.
yes, I am Om Prakash Maurya. The first one taken by another scholars, another research scholar. So he will separate. He will send the separate video, and I will send. I will send the upload. I will upload the separate video.
Okay, thank you, sir.
Okay. Okay. Thank you. Thank you. Bye bye. Right.